Welcome everyone. In our journey through Python for scientific computing, we have previously explored how to tackle single, ordinary differential equations. Today, we elevate that understanding to address systems of simultaneous first-order differential equations, a concept vital for modeling the complex, interconnected dynamics we observe in the natural world, and engineering systems, such as ecological population changes or intricate chemical reaction pathways. Our primary instrument remains the ODE function from SciPy, which we will now leverage to manage these coupled equations. By the conclusion of our session, you will be proficient in formulating a system of differential equations in Python, specifying the requisite initial states and the time domain for the solution. Furthermore, you will learn to employ ODE to derive numerical solutions, visualize these outcomes graphically, and, when feasible, validate our numerical findings against established analytical solutions. We will begin with a clear two-equation system to build our foundation, before progressing to a more elaborate three-equation model to ensure a comprehensive grasp of the techniques involved. When we extend our work to systems comprising three or more simultaneous first-order differential equations, such as tracking quantities h of t, I of t, and v of t, the process of using ODE involves several clearly defined steps. First, it is essential to specify the range of the independent variable, usually time, over which we seek the solution. This is typically achieved by creating a NumPy array representing discrete time points from a start to an end. Second, the core of our problem, the differential equations themselves, must be defined within a Python function conventionally named model. This function will accept the current values of the dependent variables, h, I, v in our case, as an ordered collection, the current time t, and any other constant parameters that influence the equations. The fundamental task of this model function is to compute the instantaneous rates of change, dh dt, di dt, and dv dt, and to return these rates as a list, maintaining a consistent order. Third, if these equations depend on fixed parameters, such as rate constants, these must be communicated from the main part of your script to the model function. ODE facilitates this through its args argument, to which you pass a tuple of these parameter values. Lastly, the starting values for h, I, and v at the initial time point must be specified as a tuple and provided to ODE. With these elements correctly configured, ODE will compute the solution trajectories for h, I, and v. Let us now apply these principles to a specific example. A system of three coupled differential equations that models the dynamics of HIV infection by tracking healthy cells h of t, infected cells I of t, and free virus particles v of t. We are provided with initial conditions. H begins at 1 million, I at 0, and v at 100. The rates of change for h, I, and v are governed by three distinct equations involving several rate constants, labeled kr1 through kr6, which dictate processes like cell growth, natural death, infection, and virus production. For instance, the change in healthy cells, dH dt, is determined by a constant production rate, a natural death rate proportional to h, and a rate of infection which depends on the product of h and v's. Our task is to solve this system and visualize the solutions for h, I, and v's over time using a semi-logarithmic plot, where the vertical axis is scaled logarithmically. The accompanying Python code first initializes the values for the six rate constants, defines the time span for the simulation, and sets the initial amounts for h, I, and v's. The model function is then constructed to encapsulate the three differential equations, calculating dh dt, di dt, and dv dt based on the current values of h, I, v, and the globally defined rate constants. Finally, ODE is invoked with the model, initial conditions, and time array. The resulting solution, which contains the time series for H, I, and V, is then plotted using semiology to clearly show how these populations evolve, which is especially useful when their magnitudes vary significantly. Throughout this session, we have unlocked a powerful capability: solving systems of simultaneous first-order ordinary differential equations using Python's ODE function. We have learned that the cornerstone of this process is the meticulous definition of a model function, which must return a list of derivatives corresponding to each dependent variable in a consistent sequence. We emphasized the importance of correctly specifying initial conditions for all variables and effectively passing any constant parameters to our model via the args mechanism in ODE. We started with a foundational two-equation system, enabling a direct comparison between numerical and analytical solutions, and then progressed to a more complex, real-world inspired three-equation model for HIV dynamics. A key takeaway is understanding how ODE structures its output, an array where columns typically represent each variable's solution over time, and how to manipulate and visualize this data, for instance, using semi-logarithmic plots when dealing with quantities that span multiple orders of magnitude. This comprehensive approach equips you to simulate and analyze a wide variety of interconnected dynamic phenomena, from biological systems to chemical reactions, significantly broadening your computational modeling toolkit.